This video is prediction part 2. We're picking up with the interpreting the intercept slide. So we're going to talk about the regression equation and how to interpret what the y-intercept in that equation means. So sometimes it will have a meaning and sometimes it actually won't. So let's look at what the slide says here. The intercept mathematically is the y value of a data point whose x value is 0. So it would make sense that the y-intercept only has meaning if the x being 0 is feasible. If x being 0 doesn't make sense for the problem, then the y-intercept doesn't necessarily mean anything. That's also the case if only positive values or negative values are meaningful for x. The y-intercept is not meaningful in context and it just makes the equation work. So sometimes the y-intercept is just there to make the equation work, and sometimes it actually has a meaning. So let's take a look at some examples. Example 5, interpreting the intercept. For each of the following scenarios, decide whether or not the y-intercept is meaningful in context. So we're deciding whether or not the y-intercept is meaningful in context for the house price example. So I went ahead and rewrote the regression equation for the house price example. So if you'll remember, this number is the y-intercept. So we want to know if that makes sense in context of the problem. So this 160.194 is actually 160,194 because if you'll remember, y is in thousands. And this is the y when the x is 0. Now 0 is the size of the house. So what this is saying is when the size of the house is 0, the cost of the house is $160,194. So does that make sense? Technically no, because the size of the house can't be 0. It's just not possible. So technically the 160.194 just makes the equation work, and it doesn't have meaning in context of the problem. Now you might say that the base price of a house before size is taken into consideration is $160,194. However, again, 0 can't be the size of a house. So again, it technically does not make sense in context. All right, let's look at the next example, the test score example. And I think I gave two, we've had two examples with test scores. This is the one where x is the score on the third test out of 80, and y is the score on the final out of 200. And that equation was y equals 4.827x minus 173.513. And for this one, negative 173.513 is the y-intercept. That's when the x is 0. So what we're saying is on the third test, when you make a 0, on the final you would make negative 173.513. Okay. The 0 makes sense. You can make a 0 on a test. You can make a 0 on the third exam. You cannot, however, make negative 173.513 on the final. It's a negative number. So again, the y-intercept just makes the equation work. It does not have meaning in context of the problem here. Let's move on. The regression equation is y equals 1.98 plus 0.039x, where x is the temperature in a freezer in degrees Fahrenheit, and y is the time it takes to freeze a certain amount of water into ice. Now, this one, notice, is a little bit backwards. Normally we have mx plus b, but the m is here. This would be the b. So they flip-flop the mx and the b. So the slope is 0.039, but the y-intercept is 1.98. So 1.98 is your y-intercept when the x is 0. So what we're saying here is that when the freezer temperature is 0 degrees Fahrenheit, and that makes sense, you can be 0 degrees Fahrenheit, the time it will take the amount of water to freeze is 1.98. I'm not sure. I'm thinking that's probably hours. But whether it's hours, whether it's minutes, this does make sense. Because you can have 0 degrees Fahrenheit, and this is a positive time. So that does make sense to the problem. So in context of this problem, what does the y-intercept mean? It means that when the temperature in the freezer is 0 degrees Fahrenheit, the time it will take for a certain amount of water to freeze into ice is 1.98. Alright, so the first two just made the equation work. The third one does have meaning. Let's check out one more. The regression equation is y equals negative 13.586 plus 4.340x. Again, they flip-flop the mx and the b. So here's the b, here's the mx. So our y-intercept is negative 13.586, where x represents the age of an elementary school student and y represents the score on a standardized test. So if the x is 0, that means that the student is 0 years old. And if they're 0 years old, they're making a negative 13.586 on the standardized test. Neither one of those seem to make sense because you can't be 0 years old and go to elementary school. 0 years old would be when you were born. And negative 13.586, that's a negative score on a standardized exam, and I don't think that's going to work either. So again, another problem where the y-intercept has no meaning in context of the problem. It just makes the equation work. Alright, let's look at example 6. The following table lists the heights in inches and weights in pounds of 14 NFL quarterbacks in the 2009 season. Compute the regression line for predicting weight from height. Calculate R, the correlation coefficient. So I'm going to let you pause the video and try this. My advice, L1, L2, and then calculate the linear regression equation along with R. Okay, so go ahead and pause the video, and when we come back, I will go over the answer. Okay, so I've gone to Stat, and I hit Enter, and then L1, and then L2. L1 I put the heights, and L2 I put the weights. So now I want to compute the regression line for predicting the weight and height. So just to recall how we do that, we go to Stat, we arrow right to Calc, we choose number 4, linreg. We put in our X list. My X list is in L1, so second 1. My Y list is in L2, so second 2. Leave everything else blank. If you have an 83 and it just says linreg AX plus B, then type in L1, comma L2, and then hit Enter. And here we go. Here's our equation. Y equals 3.272x minus 20.021 if we round to 3 decimal places with an R of 0.5628. So y equals 3.272x minus 20.021 is the regression equation for predicting weight from height. So if you put height in for x, it will predict the weight. Calculating the R is 0.5628. So do you think this linear regression model is going to be an accurate one? Well, the question has to do with the R. How strong of a correlation is this 0.5628? And it's not super strong. So I would say that it might be a little less than accurate. Just because it's not a really strong correlation that's close to 1. Is it possible to interpret the Y-intercept? So let's go back and read what each thing represents. The height is the X and the weight is the Y. So in this case, our Y-intercept is negative 20.021. So it's 0 feet tall. A football player that's 0 feet tall and weighs negative 20.021 pounds. And so that does not make sense in context of the problem. Now, if two quarterbacks differ in height by 2 inches, how much would you expect their weight to differ? So the X is the height, and that differs by 2. So to find the difference in the Y, which is the weight, is 2 times the slope. So let's go back and look at what the slope was. The slope is 3.272. So you're going to multiply 2 times that, and I believe you get 6.544. Right? Predict the weight of the quarterback who is 74.5 inches tall. Okay, so I've substituted 74.5 into the equation. 3.272 times 74.5 inches tall minus 20.021. And if I typed it into my calculator correctly, you get 223.743 pounds. Does Tom Brady weigh more or less than the weight predicted by the regression line based on his height? So let's go back and look at Tom Brady. Tom Brady is 76 inches, 76 inches tall and weighs 225 pounds. So he's 76 inches tall. So let's see what the equation predicts his weight to be. So if I substitute that into the equation, and the regression equation predicts that he is 228.651 pounds. Now his actual weight is 225 pounds. So it says, does Tom Brady weigh more or less than the weight predicted by the regression line based on his height? He definitely weighs less by just a few pounds, but he does weigh less. Okay, so example 7, I want you to pause the video, read this over. This is about blood pressures. They have systolic and diastolic. To make it fit, I had to break the table in half. So this whole thing here and here is L1, the whole thing here and here is L2. So pause the video and enter those now. Okay, hopefully you entered those. So we want to calculate R, decide if it's a strong correlation, compute the regression equation, and then see if it's possible to interpret the Y-intercept. So pause that and try those. Okay, here are the answers. The R is 0.8568. This is a strong positive correlation because it's close to positive 1. Here's the equation. The equation Y equals 0.575x plus 9.183. Is it possible to interpret the Y-intercept? Well, the 0 would be the X, so that would be 0 systolic and a 9.183 diastolic. That's just not possible. Both are way too low. Now pause again and try these two. Okay, for E, it says if the systolic pressures of 2 patients differ by 10, by how much would you predict the diastolic pressure to differ? So if the X differs by 10, we multiply that times the slope, and that'll give us the Y difference of 57.5. So the diastolic pressures differ by 57.5, which is quite a bit. And then predict the diastolic if the systolic pressure is 125. So we plugged in 125 and got 81.058. And that's it. Email me with questions.